Okay, so we saw that if we have a certain system, we take its differential equation and we look at use the Laplace transform, we end up with a transfer function which is a fraction of polynomials. And that is what we will be looking at now. So an algebraic fraction has a numerator and a denominator. And in our case, these will both be polynomials. So for example, 4x plus 7 over x squared plus 3x plus 2. Well, the degree of the numerator we will denote with n. So that's the degree of the numerator. And d is the degree of the denominator. In our case here, n is equal to 1 and d is equal to 2. Now, because the denominator is a polynomial of degree 2 and the numerator is a polynomial of degree 1. The highest power of x in the numerator is equal to 1. Now, if n is smaller than d, if n is strictly smaller than d, then we call the fraction is proper. If this is not the case, we call the fraction improper. So for example, if we have x minus 4 over x plus 2, and let's see, okay, you can still see that. We know that n is equal to 1 and d is equal to 1. So the fraction is improper. And if we take x squared plus 2x divided over x to the power of 3 plus 4x minus 1, we have n is equal to 2 and d is equal to 3. 2 is less than 3, so we have a proper fraction. Now, for now, and we will continue that, we'll continue a bit later on improper fractions. For now, we will only look at proper fractions where the degree of the numerator is less than that of the denominator. So let's return to our example. 4x plus 7 over x squared plus 3x plus 2. We want to rewrite this, and we want to rewrite it in terms of partial fractions so we can use the inverse Laplace transform and find our solutions. So this will be something of the form a over x plus 2 plus b over x plus 1. But how do we get to these partial fractions? Well, this happens to be an example of a fraction with, so we're looking at proper fractions with distinct linear fractions. Now, these two, we will show that these two are the factors of the denominator. They are linear because the power of the highest power of x is only 1, and they are distinct because these two are not the same. So, if we have a situation where we have a proper fraction with distinct linear fractions, factors, and we have a factor of the form ax plus b, so this is a factor, we will get a partial fraction of the form a over ax plus b. Now look at our denominator. We know that we can write x squared plus 3x plus 2 as x plus 2 times x plus 1. So that's why I know we have two partial fractions, one of this form, one of the other. But let's say you can't find them. Let's say they're not as easy or obvious. The partial fractions here you can also find them by taking the roots of this denominator. So the roots of x squared plus 3x plus 2 can be found like this, and we can look at the ABC formula and we will find x1 and 2 is equal to minus 3 plus or minus the square root of 1 over 2. And we will find that this is minus 2 or minus 1. Now, if we have a polynomial where the leading coefficient is 1, and I'll show you an example where that is not the case later, we can rewrite any polynomial, and I'll show you with this. We can rewrite it as x minus the first root times x minus the second root. And this works for all polynomials. You can write a polynomial of any degree in terms of x minus all those roots. Some might be complex, some might be repetitive. We are now looking at the case where they have two distinct roots. Now, if we plug in minus 1 and minus 2, we get x minus minus 2 times x minus minus 1, which is the same as x plus 2 times x plus 1, and we get the factors we found because this one can be factored quite obviously. So if we have this situation, we look at the denominator and it has two distinct linear factors. They yield two partial fractions of this form. Now, are we there yet? No, not quite, because we don't have a and b. We don't have a and b. So let us first solve this one properly and then continue on to the next case. So if we have, we know that this must be equal to that, but we don't know a and b. So how do we find a and b? Bit of a better brush. We can write this first one as x plus a over x plus 2 over x plus 1 over x plus 1. And I'm just multiplying by 1. There's nothing fancy happening here. Just multiplying by 1. And you'll see in a minute why I do that. I multiply here with x plus 2 over x plus 2, which means that now these two parts have the same denominator. We can write this as a times x plus 1 plus b times x plus 2 over x plus 1 times x plus 2. And we already know that x plus 1 times x plus 2 is x squared plus 3x plus 2. So rewriting this a little bit more, we have a times x plus b times x, a plus b times x plus a plus 2b over that denominator, which is x squared plus 3x plus 2. And if we know that these two are equal to each other, then this must also be equal to that. And as the denominators are already equal, we now only have to make sure that the numerators are equal. So a plus b times x plus a plus 2b is equal to 4x plus 7. How do we now solve for a and b? Well, here we have a number of x, and here we have a number of x, and we have a constant coefficient, and here we have a constant coefficient. So this gives us two equations. The first one is that a plus b is equal to 4, and a plus 2b is equal to 7. Now this is a set of linear equations, two variables, two equations, and we can solve them. For example, if I subtract the first one from the second one, I get 0a plus b is equal to 3, which basically means that b is equal to 3, and then I put that in the first one, and we find a is equal to 1, and I can rewrite this one, because we found a and b now. A is equal to 1, and b is equal to 3. So if we have distinct linear factors, we get partial fraction of this form. We can write that with a and b, and this is the way we find our a and b.